bugs in your own code.
So does the pointer have a scope?
Does the pointer have a scope? Yes. So a pointer is still just a variable. So a and b only exist inside of the swap function here. So yes, scope, there's no change in the notion of scope. All we've introduced is the star, and the star means this is not an actual integer, this is the address of an integer. Yeah?
What's the difference between the asterisk and the ampersand again?
Good question. What's the difference between the asterisk, the star, and the ampersand? So the star means, unfortunately, two things. When you specify a star in the prototype of a function, for instance, right here in the line I've highlighted, swap int star a and star b, in that context, you are saying a should be a pointer to an int, b should be a pointer to an int. This is identical to, well, let me not go there yet. So that's all that's saying. That is the data type of a and b. Now, in the context of the actual function, star takes on, unfortunately, a different meaning. What does star a and star b mean in the three highlighted lines now inside of the swap function? So it just means go there. So it's the dereference operator. It means go to that address. And then lastly, the syntax up here, and this is really the third and final piece of syntax, the ampersand means x is some variable. It's an int in this case. Ampersand x means get the address of x. So if I can hammer home just that one detail, let me actually quickly go back into GDB. We still have our breakpoint, even though the program stopped running. Let me run the run command again. Now I'm back in main. Let me do next. Let me do next. And let me clear the screen and just do a quick check. Print x, print y, they're 1 and 2. But now, even in GDB, I can play around with this. I can print ampersand x, and what do I get back? Well, that, in fact, is the numeric address, albeit written in hexadecimal notation, which we started looking at last week, of the variable x. So if you look at your 2 gigabytes worth of RAM in your computer, and you literally go to that address, and I can't translate hexadecimal in my head to English words, if you go to that address, you can actually see the number 1 at that location. Yeah.
I was wondering, why do you need to use do you need to use a star in like to access the value inside the pointer?
Do you need to use the star to access the value in the pointer? Yes. If you want to go to that address to find its value, you say star a or star b.
But if you just print a, that would just give you the address.
If you just print a or you just print b, yes, that will only show you the address, which for the most part is useless, unless you're using the address to actually go there.
Is that because the function is declared as a pointer?
That is correct. Because a and b were declared as pointers, simply printing a or printing b would not be useful. It might be interesting in that you can see where they are, but it would not be useful. Yeah?
So when you initially allocate spaces in memory for A and B,
Uh-huh.
know that you're not overriding something else, like something else which is more important. So when that garbage value came up, how did you get an extension for some other program?
That's a really good question. So the garbage values we keep seeing, and they're kind of a cute curiosity, but thus far they've had no downsides. But if we actually use these garbage values, bad things can in fact happen. If you have a pointer that has some junk value in it because of some previous function call or some previous execution of code, and you do star and then that pointer value, bad things will happen. In fact, let's see if we can implement this very idea really fast here. So let me open up a new document in gedit. I'm going to go ahead and save this as bad.c. I'm going to go ahead and at the top here, let's just first start doing int main void. I'm not going to bother with any command line arguments. And this is the other context in which you might use the star notation that I promised a moment ago. I can actually say to the compiler, give me a pointer to some data type. I can actually say int star p. And p denotes pointer here. But notice I do not have, in this simple example thus far, an equal sign. There's no assignment operator. So what is actually at star p? If I were to do something like this, printf %d, like print an integer, what do I want to print? Go to p and print whatever integer is there. What's going to happen? What's going to print on the screen? Yeah, it's kind of totally unclear, right? So p is a pointer, And because I've not initialized it to anything, it could be the number 0, it could be the number 1, it could be 5, 5, 5, 5, 5, 1, 2, 1, 2. It could be any number. And if I then presumptuously say, doesn't matter what it is, go there with star p, well, what if star p is in a particularly bad point in memory? It's the part of memory up at the top that is where your own program is. Maybe it's address 0, which we also said last week is bad because the null pointer is known as address 0. So in short, I dare say the most common way for crashing a program with a seg fault or with a core dump that some of you guys have accidentally induced thus far is by doing exactly something like that. Not realizing that a pointer has just some bogus value or some null value and accidentally going there, and then you get this so-called segmentation fault. So though this is a lot of new syntax, again, there are only 3 ways in which we've used the star. Here, and this is just off the cuff, we'll actually see this in more useful context in the future. Here, when you actually want a pointer, we saw it in the function prototype of the swap function, and then inside of the function itself, where you say go there by way of the star notation. And we'll see another example before long. Any other questions? Yeah?
What is the advantage of swapping values inside like as opposed to redirecting a variable to the address of that?
So what is the advantage of swapping them in the function? As I missed the end of it.
Swapping the actual values versus swapping the addresses of the values so that the variable will actually be directly different.
So good question. And if I can kind of reminisce what we did last week with the milk and OJ. When I had 2 slips of paper and I said, here's the address of the milk, here's the address of the orange juice, then I handed them to someone to do the swapping. Suppose I now receive these pieces of paper. Well, if I just said, OK, here's these pieces of paper back, it doesn't actually change the contents of memory. All I've done is kind of a switcheroo of the addresses, but the physical layout of RAM has been affected in no way. And the goal typically of swapping 2 variables is to literally swap 2 variables, not just change, the order in which we're talking about them. If that's not too hand-wavy of an answer. Other questions? Yeah?
So are the star and the ampersand kind of inverse operators? Like could it
Yeah.
be an ampersand star A or just print out A?
Perfect. Yes. So we could start to do crazy things whereby if you have, let's do this. And again, we'll see a more complete example in a moment. If I have int x gets 1, and now I have int star p, I could actually do this. Because x is an integer, and every integer, every variable is somewhere in memory. Ampersand x means find the location in memory. So int star p means give me a pointer to an integer. And what address do I actually want to put there is x. And so what I can then do is now I can either print out x like we did in week 1. And this would absolutely work. Print %d as a placeholder, print out x. But what would also work now if I wanted to print the number 1? I could also say star p. Or if you want to get crazy, I could also do, well, print x. But wait a minute. Let's get the address of x. Wait a minute. Change my mind. Star x, ampersand, star. And yes, these would invert each other's behaviors. Completely useless, very bad style. But it would, in fact, reverse the effects of those operators. So, all right. So we've now swapped successfully. It's always around this point in the semester, and you might have seen this in section already. But a quick interlude here. Now that you get this particular joke, let's go ahead and take a 5-minute break, and we'll regroup as to how these pointers can be used and abused. All right. So we are back, and recall that this is the picture we keep drawing, the bottom part of our computer's memory. And we typically call these rectangular slivers frames. And recall just a moment ago within GDB, when I executed backtrace, what I was seeing was pairs of these frames. So even though I've drawn them at different heights here, main is a frame and swap is a frame, but I've kind of divided it out here pictorially, whereby you see the parameters first, then the local variables, then swaps parameters, then swaps locals, and so forth. And this simple, relatively simple layout in this pattern is actually very easily exploitable. So I mentioned a couple weeks ago this very popular way of hacking into systems and taking over servers and defacing websites and so forth, and that very often, but not always, reduces to leveraging an understanding of all of this memory and then somehow figuring out how to inject your own code into one of these frames so that you overwhelm that frame with way more bits than it was supposed to store, and the result is that your code, not the original programmers, gets executed. But more on that in just a bit. So we had a couple of programs on Wednesday, among them compare1.c. And this program, recall, if I scroll up to just the main function, was actually flawed. Even if I typed in hello and then hello again, it said you typed different things. And what now is the simple explanation for why typing hello and then hello again yields different things, apparently? Yeah? Exactly. What we're really doing with this one seemingly correct line of code is comparing two values, but literally two values. We're comparing S1 and S2. Well, what are they? Well, recall we peeled back this layer last week and we said, you know what? This is a training wheel. This is actually char star. This too is actually char star. And so S1 and S2 are pointers to chars. What char, in fact? Well, the very first character in the string. And recall that the convention the world adopted years ago for strings in C is that all you have to remember is the address of the first character, because so long as you plant a little breadcrumb at the end, \0 at the end of the string, then you can figure out by just iterating from left to right exactly how long that string is and where it ends, and therefore when you should stop printing out HELLO. So what was the solution to fixing this problem? What's that? So put star, OK, so we could do this. We could say star S1, star S2, but borrowing the jargon from before break today, what does star S1 mean here? Go to S1, and what should we find there if I typed in hello both times? I'll find H, and then I'll find H again. So this is a step toward correctness, but unfortunately now it's going to say that any two words that start with hello, that start with H are actually going to be the same. And in fact, they're not. So we did have, recall last week, a loop where we started iterating from left to right and then just looking for difference, looking for difference, looking for difference. And if we find one difference, whether it's the string length, whether it's a character that's not quite identical, then it actually would say different. Otherwise, if we get to the end of both strings, we found nothing wrong, we can then say the same. Or an even simpler approach, and again, consistent with this idea that you need not always reinvent the wheel if someone else has put it into some kind of library and header file, we could do this. And I've actually added a bit of error checking that we didn't have last week when we did it on the fly. Recall that we introduced this function, strcomp, string comparison, and it can actually return 3 values, but we only care about one. What did it mean if it returns the value 0? Yeah, that their strings are actually equal. They're the same length. They're literally the same characters. They're equal. And recall that strcomp could return a negative number or a positive number, but that had to do with alphabetical ordering, if you actually cared about whether one comes first or last. Now, I added one check here, and this is one of these rules of thumbs that even though it might not seem all that compelling at first, take our word for it. Any time henceforth that you start using pointers, which you've actually been using since week 1, we just called them strings. We didn't call them char stars. You should always be checking if a pointer is null before you do anything with it. Because as per the conversation before break, if you've got some garbage value in a pointer, if that pointer is itself 0, either intentionally or accidentally, and you say go to this address, and that address is 0 or some bogus garbage character, you're going to induce what? Segfault. But the problem is not always. And this is why a lot of bugs go undetected by people like us, by professional programmers, sometimes for years, because not always does a mistake like this induce an error. Typically, we call these things frames, and they also refer in general to segments of memory. Typically, you're actually allowed to wander a little bit outside of the actual memory you've been given. You can go a little higher, a little lower. But if you go too far, then the segmentation fault happens. But the problem is that if you don't venture terribly far, or you just get lucky and you go to a garbage address, but that address doesn't induce a crash, you might not realize that your code is in fact flawed. So one of the things we'll introduce in a couple of problem sets is a tool called Valgrind, which is a tool like GDB that you just run at the command line, and amazingly, it will actually analyze your program for you and try, with some probability, to figure out if you're misusing pointers in some way. But for now, the approach is to be defensive, and anytime you're